Welcome to Lecture 3.4, Divisibility and Primes. Let's start with the definition. Suppose n and d are integers and d is non-zero. We say that d divides n, and we write this by putting a vertical bar between the d and the n, if n equals d times k for some integer k. In other words, d divides n if and only if there exists a k, it's an integer, such that n equals dk. Other ways to say this, you're probably familiar with, are n is divisible by d, n is a multiple of d is a divisor of n, and d is a factor of n. Let me pause to make an important and probably straightforward point about when d does not divide n. First of all, we use the same symbol, the vertical bar, but we put a little slash through it this time. And d fails to divide n if and only if n divided by d is not an integer. And here, remember that we are forbidding d to be 0. Let's do a few examples. Of course, you're familiar with division from grade school, but I think it's worth checking out some of the interesting, non-obvious cases of this definition that maybe didn't arise in grade school. Okay, so first of all, I claim that every positive integer divides 0. So the discussion of whether 0 divides things or things divide into 0 may not have come up when you first learned about this, but I claim that any positive integer d divides 0 because 0 equals d times k. We can find a k that makes this work. Just pick k to be equal to 0. I also claim that 0 does not divide into any positive integer. Now, I've actually disallowed this with the definition, but one reason why it's convenient to do that is because it wouldn't work anyways. Let's just check. So, does 0 divide into n? Well, if this were to be the case, then we would need n to be equal to 0 times k for some k, and there does not exist such a k. So everything divides into 0, but 0 does not divide into anything. And also one more thing, using this definition, let's just check, would 0 divide into 0? So 0, you can make the case that it does, because 0 equals 0 times k. You can certainly just set k to be equal to 0. Although, in this definition, I have explicitly said that d is non-zero. And that's because we don't really like to talk about things like 0 divided by 0, because that's just opening a whole can of worms. You know, there are some people who would call this 0 because 0 is on the top of the fraction. Some people say it's infinity because 0 is on the bottom. And other people just cancel the zeros and like to say, well, this is equal to 1. They have the most positive outlook on life. But this is not allowed, so we usually don't allow we don't even want to talk about this, which is why it's really why we do require that d is not equal to 0. It doesn't mess up these two cases, but it does mess up this. Our next example, every positive integer is divisible by 1 and itself. This is straightforward to check. So if we have an integer n, 1 divides n because n equals 1 times k. Well, we can just set k to be equal to n. And also n divides n because n equals n times k. For some k equals 1. Finally, the only divisors of 1 are 1 and itself. So if d divides 1, then that means that 1 equals d times some integer k, and there's no way that we are going to be able to solve for a d and a k that are integers unless d and k are plus or minus 1. So they're either both -1 or both +1. Let me now turn our attention back to prime numbers, something that you're familiar with, I'm sure, from grade school, once again. And also, if you watched earlier lectures, I think I introduced a formal definition a few lectures ago. So recall that an integer, p bigger than 1, is prime, so we're right away excluding 1 from being prime. Also, we're excluding 0 and negative numbers from being prime. If p equals a times b implies either p equals a or p equals b. This is probably not the definition that you were given in grade school. So let's actually write down that definition as a theorem. An integer p bigger than 1 is prime if and only if its only positive divisors are 1 and p. Let's prove this. So because this is an if and only if, we need to prove both the forward and backward implication. So let's prove the forward one first. So suppose p is bigger than 1 is prime. What should we do? We have to show that its only divisors, positive divisors, are 1 and p. And so let's take a positive divisor and let's show that it has to be 1 or p. And d is a positive divisor, so d divides p for, maybe I don't need to say for some positive d. So let's just follow our nose and write down the definition for what that means. So then there exists some integer k such that p equals, so d times k. Okay, so now it's tempting to use what we know is true, which is the result, and we don't want to do that. Let's just use the definition of prime, and that's convenient. If p equals ab, well, that's exactly what we have right here. So we conclude that either p equals a or p equals b. Then p equals d or p equals k. So if p equals d, well, the only positive divisor is p. That's what we want. So, or if p equals k, that means that d has to be equal to 1, i.e. d equals 1. So we conclude that our divisor d, that's positive, is equal to p, or it's equal to 1. And that confirms that direction. Next, going backwards. Now let's suppose that for a positive integer p, its only positive divisors are 1 and p. Let's write that down. So let's suppose p is bigger than 1 and its only positive divisors are 1 and p. Okay? So what are we trying to show? We're trying to show p is prime. What does that mean? It means this definition here. So we need to show that. So let's suppose that p equals a times b. So let's write that down. Oops, let me use a different color. Suppose p equals a times b. And now the only positive divisors are 1 and p, which means that then either a equals 1 and b equals p, or a equals p and b equals 1, I should say by assumption. In either case, we conclude that well, so look what we just wrote down. Equals either P equals A or P equals B. So, i.e., either P equals A or P equals B. So P is prime. And that completes the proof. And just to hammer home this definition, which seems a little more contrived than this one, but I think it's probably mathematically cleaner. This is easier to understand. Let me do an example. Let me do a non-example. Let's do two examples. An example and a non-example. So, first example, if P equals 7, then anytime we write 7 equals A times B, I hope you agree that either A equals 7 or B equals 7. And here I should assume that assuming A and B are positive. And a non-example is 6. So if 6 is equal to A times B, it's not necessarily true that A or B must be equal to 6. What if 6 equals 2 times 3, for example? Next up are two statements on divisibility that both seem like they should be true, but I'll tell you right now in advance that one of these is actually false. Let's see if you can figure it out before I tell you. Suppose we have three integers, a, b, and c. The first one says if a divides b and b divides c, then a divides c. Seems reasonable. Let's check the second. The second says if a divides b and b divides a, then a equals b. So which one of these is true and which one is false? Pause the video if you want to try to figure it out, because I'm about to tell you. Okay, you got it? The first one I'm going to prove. In other words, that's true. Did you get it right? Okay, so if a divides b, then that means that b equals a times k for some integer k. Similarly, if b divides c, then that means that c equals b times l for some l, some integer l. Now remember what we're trying to prove. Let me write it on the side. So we're trying to prove that a divides c, so this is sort of our thought bubble, and that means that c equals a times some integer. You see what integer we're going to use? Let's try to put these together. So then c equals b times l, and b is a times k, which is a times k. I guess I'll write the l for it. Well, a times kl. There we go. And since k times l is an integer, that means that a divides c. c is a times some integer, so that answer up here is k times l. So that means that a divides c. Okay, that's the proof of the first one. The second one, if a divides b and b divides a, then a equals b. Well, to show this is false, all we have to do is find a counterexample. So what about 2 divides negative 2? And that's true. Even though negative 2 is a smaller number, this holds because negative 2 equals 2 times negative 1. So, and similarly, negative 2 divides 2, but 2 does not equal negative 2. So something close to this is true. I think if this holds for the integers, and I think a and b differ by at most plus, they're either the same or they're plus or minus 1. Though I encourage you to check that. There might be strange things that happen if 0 is involved, but I don't think so. I think that's something that we could prove. In fact, yes, that's another reason why we don't want to say that 0 divides 0, because if we did, we would have a counterexample to that. We could say that 5 divides 0 and 0 divides 0, but 0 is not equal to 5. But we don't want to say that, so we don't allow this to be true. On the previous slide, we just demonstrated that divisibility is transitive, and I'm going to use that to prove this seemingly simple proposition that every positive integer bigger than 1 is divisible by a prime. Again, this should not seem like a surprising result, but we have to make sure that we use our definitions. Okay, so how do we get started? So let n be bigger than 1. I don't really need to write that down because I'm saying that, I'm assuming that, but it doesn't hurt. There's two cases. Case 1 is that n is prime. In this case, n divides n, so n is divisible by a prime, namely itself. Nothing really more to show. Case 2 is that n is not prime, and then in this case we can factor it as n equals, let's say, a naught times b naught, where a naught and b naught are, I should say, they're bigger than 0. I really should say that they're bigger than 1 and smaller than n. So we can always write 1 times n or n times 1, but if it's not prime, that means we can factor it like this. Because remember what prime means. Prime means that if n equals a times b, then n equals a or n equals b. So if it's not prime, that means that that we can find an a and b for which one of these fails. Okay, so now we can ask, are either of these prime? If yes, then we're done. If not, well, we can keep going. So how do I want to write that? So if a naught or b naught are prime, I really should say if either one of these is prime, we're done. Clearly, that divides n. Otherwise, we can take either one of them. Let's just take a naught. We can write a naught as a1 times b1, where, now I'll do it right this time, a1 and b1 are between 1 and n properly. And we can keep going. If a1 or b1 is prime, then, well, by the transitivity of divisibility, then by transitivity, I really should say, let me just remind you what this is, then a1 divides a naught, and a naught divides n, so a1 divides n, and we're done. Otherwise we can keep going. We can keep going. So, in other words, write a1 as a2 times b2, where a2 and b2 are between 1 and n. And then at some point, this process will terminate. So this process must terminate after finitely many steps and why is that? Well, it's because we're starting with n, and then we're getting a naught, which is smaller, and we're then getting a1, which is smaller than that, and then a2, and then all the way down to all of these are bigger than 1. So there's no way that we can have this infinite descent of integers from n down to 1. So at some point we need to have some ak like this. So let me just say, i.e., ak must be prime for some k. If it wasn't, we could just keep factoring it, get smaller and smaller. I would say by transitivity of divisibility, ak divides n. I think I could elaborate more by doing this k steps, but I think it's fine to just say this. And so we're done. That's the end of the proof. We'll conclude this lecture with something called the fundamental theorem of arithmetic. And it's got fundamental in the name because it's so straightforward that you probably don't even question why it's true. But I will finish by showing you related number systems to the integers where it actually fails. Okay, let's get started. This result says, given any integer n bigger than 1, there exists some number k, distinct prime numbers p1 up to pk in increasing order, and positive integers, these are exponents, e1 up to ek, such that n equals p1 e1 times p2 to the e2 times all the way up to pk to the ek. Moreover, the sequence of pi's and ei's is unique. So what is this saying? Sometimes when you see a mathematical statement like this, you sort of have to unravel it, and more often than not, what it's actually saying is more straightforward than it seems notationally. So this is just saying that every positive integer can be factored uniquely as a product of primes. And we're listing the primes in increasing order so we can say they're unique. Otherwise, we could shuffle around the order, and we don't want to do that. So of course this is true. Positive integers can be factored uniquely by primes. As I alluded to earlier, though this seems obvious, there are other sets of numbers for which it fails. For example, the rational numbers do not have primes or unique factorization. You know this, something like 1 equals 2 times 1/2, or 4 times 1/4, or 2/3 times 3/2. So think about what it would mean for a rational number to be prime. That would mean that q equals a times b implies q equals a, or q equals b, which of course is absurd. We can always factor these many different ways, infinitely many ways. Okay, so maybe that's not a great example, but let me give you a more subtle one. Consider the following set of numbers that we'll call R-5. These are all numbers, complex numbers, of the form a plus b root -5, where a and b are integers. If you prefer, you can write this as a plus 5bi, where a and b are integers. So it's sort of like the complex numbers with integer coefficients, but there's also a 5 in front. These are examples of what we call algebraic integers. They are roots of degree 2 polynomials, and they come up a lot in number theory. These have been well studied, but there are still some very basic open questions about how to factor these numbers in these types of sets based on this this subscript -5. So similarly, we can define things like this for many other numbers. There are some details depending on how the number factors, what the remainder is modulo 4 that I won't get into, but if you want to Google algebraic integers, you can learn all about them. Okay, so why am I showing this to you? Well, there's a basic property that the integers have that fails in this set of numbers. So 9, as we all know, can be written as 3 times 3. This is how we factor 9 as a product of primes. And we can't factor 3 any further. However, if our universe, instead of being the integers, is this set of numbers, and by the way, this contains the integers. If you let b be equal to 0, you get an integer. Well, here, 9 also factors as 2 plus root -5 times 2 minus root -5. So what does that imply? I claim that that implies that 3 is actually not prime, which is strange because there's actually no way to factor 3 further. So we say that 3 is an irreducible element, which happens to not be prime. And that's something that earlier in this lecture we proved that if we have a number that's prime, then it can't be factored further. So in more interesting sets of numbers, basic properties that we know and love can fail. So let me go into this for fun just a little bit more. So recall the definition of a prime. So P equaled A times B implies that P equals A or P equals B. Turns out that for general sets of numbers, these are actually called rings. They're sets of numbers that have addition and subtraction and multiplication, but not necessarily division. And then basic properties like distributive law and associativity. We actually have to define prime to be slightly different, a little more general. It seems like it should be the same. So this is so what does it mean to be prime? It means if P divides A times B, then P divides A or P divides B. And I won't get into why we need this more general definition, but let's just check the integers as we did before. So if 7 divides A times B, I hope you will agree that either 7 has to divide A or 7 has to divide B. And if 6 divides A times B, well, there's no analogous conclusion because we could have 3 times 2, and 6 does not divide either. Okay, so this is going to be our new definition of prime. So now what? Well, 3 divides 9, right? Which is equal to 2 plus root -5 times 2 minus root -5. So 3 divides, call this A, call that B, but 3 does not divide 2 plus root -5, and 3 does not divide 2 minus root -5. So 3 is not prime, because this property does not hold. It divides 9, but does not divide these two factors of 9. So 3 is what we say is irreducible, but not prime. So if this is something that interests you, I encourage you to take a class in either in abstract algebra, which is the study of sets with generalized operations. So this is an example of a ring where you have addition and multiplication. Or a class in number theory. These come up in number theory because they are sets of complex numbers, and one thing that people want to study is properties of divisibility and factorization. And when do things like properties that we know and love, the fundamental theorem of arithmetic, when do they fail and why? Okay, so I think that is all for this lecture. Next time we will look at rational and irrational numbers and some of their basic properties. So stay with us.